Okay, so I'm gonna give you a few seconds, start this, and pause the video and start. And once you're done, or you want to check on anything, continue the video. Okay, so let's start. We are given the formula, we're given the equation, the what do you call it, the overall dissociation equation. There's a double arrow over here. Ka, we're given the concentration of NaOH, the number of moles of the oxalic acid. We asked for the volume. We're told it's a full neutralization reaction. So the number of moles of H plus equals the number of moles of OH minus. However, to continue and say the same thing for the acid and the base, you have to make sure of the stoichiometry. So let's write the equation. H2C2O4 reacts with the base NaOH. Single arrow because one of them is strong, and here we have a strong base, to give C2 with the sodium, NaC2O4. Here you have 2 minus, here you have plus, so Na2 plus H2O, and here you have 2 with, so you need here 2, as you can see, so 2 gives 2. 2H plus with 2H minus gives you 2H2O. And from this we can get there's a 1:2 ratio, and it's important we need to know the coefficients. So to do this with acid and base, so H plus, to replace this with acid, which is in this case oxalic acid, you're gonna have to divide by the coefficient. So over 1 equals the number of moles of the base over 2. So the number of moles of the base equals to 2 times the number of moles of the oxalic acid. And the number of moles of base is nothing but the concentration of the base times the volume of the base equals to 2 times the number of moles of the oxalic acid. We want the volume of the base, so just solve for that. So 2 times N-oxy over Cb. And that's it. Just substitute, you're going to get 0.0500 liters, or decimeter cubic. And that's it for this one. You want the equations for this part. So the equations are going to be, let me change color. So it's going to be H2, the first dissociation equation, H2C2O4, partially dissociates to give H plus HC2O4 minus. How do you do this? If you haven't got the hang of it, you just give an H plus, and what you're left with basically. So let's do it with this one, HC2O4 minus. It partially dissociates to give H plus. You lose this, and you have now on top of that another minus, negative charge, so plus, you don't have any H's anymore, C2O4 2 minus. You add up the equations, you're gonna get H2C2O4 partially dissociates to give 2H plus. These cancel. You continue by adding this C2O4 2 minus. Each one has its own K. This one has Ka1, this one has Ka2, this one has Ka. I'll just call it Ka. So the value of Ka is over here, not because they're both called Ka. It's a coincidence I called it Ka, but it's because this is the overall, and this is the, again, I repeat, this is the overall. So so this is the Ka for that, and we're given the Ka2, the second dissociation constant for the acid, and we're asked to find the first one. Simple. When you add the equations, you're gonna have their multiplication being the K of the sum. So it's gonna be like this. So the one is gonna be Ka over K2. You're gonna get 0. Or you can actually get 5.9 times the power of minus 2. Why did I put 0? Because in the answer, I think they modified this into 0 here. So they're like 3 significant figures. Anyways, so let's do C. To do C, I need space, so I'm gonna just erase this. You have a video, so you can always replay. So we're asked to calculate Kb when we are reacting, or if we're dissociating the solid NaHC2O4. I want the important part, not the spectator ions, so I'm going to look at HC2O4. When it reacts with water, it could either react as an acid or a base. Here we're asked for Kb, so we're making sure that we are having a base. it's going to behave as a base. It's going to be partial dissociation. None of them are strong acids or bases. So you're going to have here C2O4 to, oh sorry, it's acting as, again, Kb. So it's giving you an OH minus. So it's receiving a proton. So H2C2O4 plus this. You can see it's balanced. And which equation correlates or has these species over here? Even though they have an OH minus, I just want the species. You have them over here. So in fact, as we have heard many times, K of the acid times K of the base equals 10 to the power of minus 14, which is K water. So since we have Ka and we have K water, it's a constant, you could say, for the temperature 25, it's going to be the same. 25 degrees Celsius, it's going to be Kb equals K water over Ka. We have Ka, which is K1. Again, I repeat, we chose this equation because these are the species we want. So we want to use this Ka. So we're going to do K water 10 to the power of minus 14 over Ka, which is what we had last time. Yeah, what we had last time. So you're going to get, if I'm not mistaken, you're going to get 1.7. Again, you hear how many? Yeah, I guess you're going to do 3. 1.69 times 10 to the power of minus 13. Very, very small. Yeah, since it's behaving as an acid for the most part, so it's gonna be expected to have a small what do you call it, Kb value, because it's an acid, more of an acid, less of a base. So sketch the titration curve of the oxalic acid with the base, the strong base. You're gonna have, first of all, what type of protic acid it is. It's a diprotic, so you're gonna have 2. How many are those? This is not related, but we can use this graph. We can actually use this graph. It's pretty much this graph actually, because it's the same idea. They're both diprotic. So it's just gonna be a little beginning in the beginning. It's not like this. Why? Because you're starting with what? You're starting with an acid or a base. You're starting with an acid. It's the oxalic acid. So you're gonna start from some pH that's acidic. So you're gonna start from down. You're gonna have some notch, and then you're gonna have a slow at half equivalence point. You're gonna have a vertical section, small vertical section, again notch, and then this, and yeah, and that's it. It's basically what you have here because you have a diprotic acid. So they're both same case scenario. Now let's solve this question instead. We've done this. So this question, we want the significance. We want to describe. These are the equivalence points. These are the half equivalence points. This is the first half equivalence point, second half equivalence, first equivalence, second equivalence. Because each section, this one and this one is when you have the first equation, which is basically H2 if you want to know. H2SO3, this is to give H plus HSO3 minus. And then the HSO3, oh my god, HSO3 minus dissociates to give H plus SO3 2 minus. So this is basically what's happening right here. So the first H plus here and the second H plus here. So you have, yeah. If it's triprotic, what you're going to have, as you might have guessed, you're going to have 3. So like that. You're going to have like that, and then like this, like that, and then like this. I can't do it. Anyways, so you're going to have 3. You're going to have 3. And we're done with this page. Okay, so let's start this, or if you want you can have a few seconds to think about this, and in a few seconds I'll start. Okay, so calculate the pH of the solution in beaker A. Beaker A has a strong base, so you got the concentration of OH minus is equal to the concentration of the base, since again 1 to 1 and strong, so concentration of OH minus is 0.2. And you have 2 ways you can do this. You can either do a concentration of H plus, which is K water, over the concentration of OH minus, or and pH equals, of course, minus log of the concentration of H plus. And or, like, another way to do this, or you can do this by simply finding POH, since you have the OH, concentration of OH minus, so minus log of the concentration of OH minus you have, and then pH would be minus 14 of that, or 14 minus that, yeah, POH. So either of those, I think this will give you 5.00 times the power of minus 14, and here will give you the 13.3, and this will give you, I think, 0.7, and this will give you the, again, the 13.3 if you subtract 14 from that. So either of those are useful, either of them will do the job. So I'll delete to get some space. You can always refer back to this in the video. So given that Ka is blah blah blah, we're asked to find the expression. So we're talking about the dissociation of HF. It's a weak acid, so we're going to have partial dissociation, so we're going to have double arrow, so H plus F minus, and the Ka would be concentration of H plus times the concentration of F minus over the concentration of HF. And we are asked to find the pH in the next part of the beaker in C. So I guess we're talking about C this whole time, or like not this whole time, but like in part B. Let me remove my mouse. Okay, so we're asked for the pH. So let's refer back to Ka. What's the useful one? The most useful term in here is H plus, because this can directly give us the pH. So to find the pH from the H plus, we need to find the concentration first. So how do you do that? Since we have a partial dissociation, we have equilibrium, and do we have the initial concentration of one of them? Yeah, we do. So we can do this way. So we can do an ice table, and then you have your HF partially dissociates to give H plus and F minus. And so we have the initial 0.2, and here we have nothing, and here we have minus X plus X and plus X. Here you're going to have XX and 0.2 minus X as equilibrium concentration. And so the expression becomes X squared, as you can see, over 0.2 minus X. And we have the Ka right here. So you can solve for this. 6.6 times the power of minus 4 equals to X squared over 0.2 minus X. So the next step is you assume that X is way less than 0.2. Because if that's the case, you can just, negligible as compared to 0.2, so just 0.2 times this. So X equals 0.2 times 6.6 times the power of minus 4, all under the square root. You're gonna get, I think, around 0.011. And this is what, don't forget, what's your X? Your X is either the concentration of H plus or the concentration of F minus. Say you want to find this, for example, you know your X, you can instantly find this. So always keep in mind what is X. So X is either this or this. This is what matters me, or this what matters to me. So it's the concentration of H plus is X, as you can see here, and so pH is minus log of that, 0.011. Let's do this right now. So minus log of 0.011. You're gonna get around 1.96, and yeah, that's about it. So I'll delete again for some space. And what do we need in C? Write the reaction occurring in beaker B. So what's happening in beaker B? Beaker B, we have a salt, NaF. So is it basic, acidic, or neutral? Well, you have to look at its components. What gave it? Where did the cation come from? Where did the anion come from? Which acid or base? So Na, immediately you think of NaOH. F, what do you think of? HF. So we have a weak acid and a strong base. So this is by nature basic. So since it's basic, we're expecting basic reactions. So if it's with water, we're expecting the salt to behave as a base, because it has basic nature. But what exactly in the base or in the salt acts as a base? It's the anion, and it's with water. They just like immediately threw it at you and said reaction occurring in beaker B. There's nothing that's added. So the only thing you can think of is water. So you're gonna have the base, the one acting as a base, so F minus plus H2O. Again, partial reaction because neither of them are strong. They're both weak. This is weak in everything. Weak as an acid, weak as a base, and this is a weak base. So yeah. So you're gonna have HF, its conjugate acid, and the OH minus. Since it behaves as a base, it's gonna show us why it's considered one. So either you look at the OH minus, giving OH minus, or accepting a proton. So find the value of Kb for the reaction you wrote above. So keep this in mind. Whenever you talk about Ka, Kb, you can always reach to one knowing the other. So Ka times Kb equals K water. Do we have Ka? Ka is what? Ka of the acid. What acid are we talking about here? The acid would be HF. Do we have Ka of HF? Well, this is all one question. So you can refer back to either of the parts, so you'll find that there is the Ka of HF. So just Kb equals K water over that 6.6 times the power of minus 4. And K water itself is 10 to the power of minus 14. So just instantly do 10 to the power of minus 14 over 6.6 times the power of minus 4. You're gonna get 1.51 stuff like 1.52 times the power of minus 11. Yeah. And yeah, that's it for which one are we doing again? Double I. For triple I, we are mixing B and C. B is a basic salt and HF is a weak acid. So in this case, what matters is there's Na plus, F minus, and HF. So the F minus and the HF, you can think of them as friends. One of them can be the conjugate of the other, whether acid or base. So F minus is going to be the conjugate base of HF, and HF being the acid. Or you can think of F minus as the base and HF being the conjugate acid. So either way, you're mixing them together. So you're going to get definitely a buffer in this case. Since it's a buffer, we have a special equation. So pH equals pKa, in other words, minus log of Ka, same as pKa, equals, plus log of the concentration of the base, which is F minus in this case, over the concentration of the acid, which is HF in this case. So we're mixing, don't forget, these are the values. Don't forget these given. These are important. So we're mixing 0.2 with 0.2, so F minus and HF. So you're gonna have the concentrations to be here the same, because F minus is gonna get its concentration from NaF. It's an ionic salt, and here we have HF. So 0.2 over 0.2 is 1. Log of 1 is 0. So I'm gonna immediately start with pH equals minus log of this. So minus log of Ka, which is 6.6 times 10 to the power of minus 4. And this is 0, because it's minus a plus log of something over something. They're both equal. 0.2 over 0.2, 1, log of 1, 0. So yeah, equals minus log of 6.6 times 10 to the power of minus 4. You're gonna get 3.18. And so we're done with that part. So now we're doing D. So we're adding A to what we got in B and C. And what is A? A is a strong base. So it's going to react with the acid. Which one's the acid? It's HF. And so we had a buffer, but what's happening here? We're adding OH minus to the acid, HF. And we're going to have a single arrow because one of them is strong. We have an OH minus right here. If you have an H plus and a weak base, same thing, single arrow. So either of them being strong will give you a single. If both of them are strong, definitely single. So single arrow gives F minus, and H plus and OH minus gives you water, H2O. There's an F minus here. Maybe I should have erased, but anyways. Yeah. So how much do you have from the H plus? OH minus. You have 0.2, and here you have 0.2. And the react ratio 1 to 1, and it's a single arrow. Both of those will be fully consumed in the end. And this will be 0.2, and again, water does not matter here. You know, it's the solvent. It's everywhere. it's, you know, in excess concentrations beyond imagination. So here you're gonna have 0.2, and like here, like it doesn't matter, but here you're gonna get 0.2. So the point is, these will be fully consumed. You're not gonna have a buffer solution anymore. To be honest, here you had 0.2 again from this, so actually they add up to 0.4. So 0.0.0.2, these react fully consuming, producing more by 0.2, so 0.4. And these are fully consumed, so you don't have a buffer anymore. So no, it's not a buffer. These fully reacted, and you don't have any HF left, so F minus is alone, so no buffer. Find the concentration of F minus. Well, in this case, you work with number of moles. So let's do this, but instead with number of moles. Since we're adding volumes, don't forget that we're adding volumes. So the number of moles, you're gonna have, how many moles do we have? So we have the volume, 50 milliliters for all, and we have the, for all of them to be 0.2, right? Yeah. So 50 times 0.2 times 10 to the power of minus 3, you're gonna get 0.01. Just a second. So when you're adding the solutions, work with number of moles instead, because you know the volumes are additive. So the number of moles is going to be of any of them, because they have all the same concentration, same volume. So I'm going to do it for one, for any of them. You're going to do 0. Or you can say 50 milliliters times 0.2 the concentration. This is concentration, this is the volume. And I want to change it to this to decimeter cubic, because this is in milliliters, so times to the power of minus 3. You're going to get something around 0.01, not around actually, exactly 0.010. 0, I think, another 0. Yeah. Anyways, so this is the number of moles for all of them. So this is 0. Because they're all having the same, you know, same concentration, same volume. So this is the initial for all of them. They fully react to produce 0. If you want, you can do it like this: minus 0.0110 and minus 0.0100. So plus 0.000. So you're gonna get here finally. Yeah. So here you're gonna get finally 0.0200. And so that's the number of moles. You have the volume, they add together, so you're going to get 150 milliliters, so same as 0.15, and that over the number of moles, you're going to get the volume, what's wrong with this? The volume, which is 0.02 over 0.15. And so you're going to get 0.133 molar. And so we're done with the question 1. Okay, so for number 2, part A is asking for the net ionic equation of the reaction, and we have this. So we can think of it like this: products, reactants, and this is dissociating to give H plus and F minus. But here they have H3O plus because they're using water in their equation. So you can either have this or this. And for the sake of balancing, it will be this. And since it's giving its H plus, and there's only one other reactant, so it's going to be the only one that receives it. So it's going to be H3O plus, and this is F minus. So we're done with the net ionic. If you want to write the states, fancy. This is liquid, this is aqueous. Find the pH. We're given the concentration of HF. We're given Ka. Looks like to me an equilibrium, an ice table kind of thing. So we're gonna do ice table. Ignore the H2O. I've done this a few times, to be honest, when I was solving. I end up writing something here. Ignore the H2O. So, like, don't even need to put this or whatever. It's just completely ignore it. So, since it's in huge quantities, it's the solvent. It's whatever dissolves in it. So, we're given the initial of HF, initial concentration. So, but we prefer working with. Never mind. Let's continue. Yeah. So 0.2. 0.50, 0, and here we have nothing, nothing. You're gonna subtract x, you're gonna have add x and add x. You're gonna have x, 0.25 minus x. And so the Ka is gonna be x squared over 0.25 minus x. And we're given Ka minus 4. We can easily do this. Assume that x is less than 0.25. Oh, also, I think I forgot this in the previous part. You need to show that you validated your, again, there's no written so far, but if there was written, you need to show that you validated your assumption. So you say that, let me show you. So yeah, let's solve for x. X is equal to the square root of 0.25 times 6.6 times the power of minus 4. Let's calculate this together. So 0.25 times 6.6 times the power of minus 4. You're gonna get 0.013. You work with, I mean, since they put the k in too, but like I don't know. Anyways, let's just keep it 1.3. If you want, you can follow the marking scheme, but this is the way of solving anyways. So this seems like to me is way less than 0.25, or I think I've heard that they said that it's less than by 0.1, like it's smaller than 1%, oh no, sorry, 10% of 0.25, so you can try that out. So 10%, so 0.1 times 0.25, you get something small. So it is indeed smaller, so 10% of this, because I've heard they said it once, smaller than 10%. But anyways, so you're gonna get a really small number. You're gonna get this, and this is bigger than that. So this, our x is smaller than this, so we can, our assumption is valid. So you actually don't need to say this, just be like, assumption is valid. Assumption valid. And anyways, you continue. So what's x? X is the, which one's important? What are we looking for here? We're looking for pH. So we're looking for the most important one, which is H3O+. So concentration of H3O+, which is equal to, actually let me do it right here. So equal to 0.013, which is again the concentration of H+. So we have H+, so we can talk about pOH. And we are done. Just put this in the calculator and you're done. So 0.013. How much do you get? You get 1.89. Now we want the net ionic for the reaction if you're adding KOH. Okay, so which one's important? It's going to be the OH minus. How is it going to react? We have an acid, we have a base, so it's going to be OH minus plus, what's the acid? HF, to give F minus and H2O. If you want to be fancy and add the states, and we're done. That's the perfect ionic equation. So what's the next one? The next one is D. So student titrated, we're given now volumes. So titrated this volume with this concentration of HF, with this volume and this concentration. So it looks like very easily you can get the number of moles for both of them. So they're asking the most basic question. They're asking number of moles of KOH. You're given both of these. So the number of moles is nothing but the multiplication of the two of KOH equals the concentration, so 4.65 times 0.87. Don't forget this is in milliliters, so for me I always multiply like this to always convert. So 4.65 times the power of, oh yeah, I guess times the power of 3 times 0.87. You're gonna get around 4.045. With how many I'm working with? So with the, yeah, so 4.05 times 10 to the power of minus 3 moles or mole. Anyways, so determine the concentration of H3O plus in solution after the addition of the base. So it looks like you're talking about equilibrium, which is the case. Or wait, no, actually it's a strong base, it's not equilibrium. But you still need to know like how they reacted. So you can do it like this: OH minus plus HF, you know, complete single dissociation or reaction actually goes to completion. So F minus plus H2O, and here you have the what we got. So 4.05 times the power of minus 3 the HF is gonna be just calculate it. Let's do that. So 25 times 10 to the power of minus 3 times 0.25. You're gonna get 6.25 times to the power of minus 3. This does look like the I stable, but it's not, since we don't have even equilibrium. But the whole point of it is just to show how much reacted by and blah blah and all that. So if you want to minus, you're gonna minus this, since it's the smaller one. Like if they completely react with a ratio of 1 to 1, this will finish before that. So you're gonna subtract by 4.05 times to the power of minus 13 or 3 minus 4.05 times to the power of minus 3, and here you're gonna have plus 4.05 times to the power of minus 3. And so here you're gonna have nothing, negligible. Here you're gonna have what's left, no need to calculate that, I don't think it matters. And here you're gonna have 4.05 times to the power of minus 3. Actually no, actually we need to know that. Yeah, so let me calculate that. So 6.25 minus 4.05. Okay, so we get 2.2 times to the power of minus 3. And yeah, so now we have HF and we have F minus. Looks like a buffer to me. So the equation will be at pH equals minus log of Ka plus log of the concentration of the base, which will be in this case F minus, over the concentration of the acid, which will be HF. So Ka is going to be given from the other one, the other 6.6 times to the power of minus 4. Okay, so I got that memorized. So minus log of 6.6 times to the power of minus 4 plus the concentration of F minus. We have the number of moles, so we can get the volume. The volume is going to be, since you're doing this with this, you're going to add them. But when you add them, you're going to get a certain volume in which these two exist in. They exist in the same volume, under the same volume. So dividing n over v over n over v will get these v's cancelled because they're the same. So you can instantly do n over n. So log, what's the n for that one? So it's 4.05 times to the power of minus 3. Actually, don't need to write it again. These will cancel the 10 to the power minus 3. They're the same. They'll cancel 2.2. Okay, so let me do this. So minus log of 6.6 times 10 to the power of minus 4 plus log of 4.05 times over 2.2. You're gonna get around 3.45. Yeah, around 3.45. Yet we're not done. We're not done yet. We found the pH. Can we get the H plus, which is the same as concentration of H3O plus? So it's just gonna be, if you want me to write it like this, concentration equals concentration of H plus, which is equal to 10 to the minus pH, which is what we found, 3.45. How do you get 10 to the minus if you don't know? If you know the minus log of the concentration of H plus, and you know that in math, if you were to take rid of ln or log or whatever, raise it to the power of the base, and minus just goes with a minus, so minus, and then 10 to the minus, immediately get that. So that's just for you to know how it came to be if you don't. And so yeah, 10 to the minus, just let me put that in the calculator, 10 to the minus 3.45. You're gonna get the concentration to be 3.55 times to the power of minus 4. And yeah, 55. Whoops, I squared. Yeah, 3.55 times the power minus 4. And here you're gonna determine the OH minus. We have the H plus, so it's easy. Just K water, or yeah, concentration of H plus, concentration of OH minus, equals K water over the concentration of H plus. And yeah, that's it. So 10 to the minus 14 over this, you're gonna get 2.81 or 82 actually times to the power of minus 11 times 10 to the power of minus 11. And we're done with part 2, question 2. Okay, so for question 3, let me delete these. So for question 3, grade 12 student, blah blah. Okay, so which solution? Okay, these questions are really easy. So, which solution was transferred to the conical flask at the beginning of the experiment? So you're gonna have a conical flask. Ignore my horrible drawing, but you're gonna have like a conical flask. I don't know why I can't make it look nice. Yeah, you have a conical flask and you add to it something, and then you have the burette and you're gonna titrate something into it. So what is initially in here? You're gonna determine from this. The pH is so low, it's below 7 and it's so low, so it's gonna be an acid, but if you want to be accurate, a strong acid, since it's way too low. So we're expecting a strong acid, but you don't really don't need to know strong, but like it's easy to know. So we're expecting an acid. Which one is it? Base or the acid? It's gonna be the acid. So you have HBr first. Which one do you start, or which one was transferred to the conical flask at the beginning of the experiment? The HBr. Justify because the pH is less than 7 or even 1, which is super strong. So indicate the equivalence point at which with a circle in the above titration. So equivalence point, it's where you have the vertical section. So you have the vertical section over here. It's useful, I repeat, it's useful, you don't need to know it, but it's useful to know that you're reacting a strong acid with a strong base. Instantly pH is 7. So just follow pH is 7 and go like that. Because you could be like, it looks like, doesn't it look like here, or maybe here, or somewhere in between, or it looks like, say here, right? Somewhere else you can say, yeah, but like you can instantly be like strong with strong, so immediately 7. You get the most accurate result. So I don't think even they might give you a range because it's strong with strong. So calculate the number of moles of titrant that have been added. So we have the volume, we got the volume instantly. This is the burette, so the volume of the titrant, so the base, so KOH. So we have the volume of KOH. And we have the pH. What do we also have? We have the, the equivalent volume, equivalent concentration. So we want to find the number of moles. So yeah, that's easy. So we have 15. That's the volume, number of moles of the base, KOH. It's going to be its volume times its concentration, which is 0. I have to go back again. 0.1, right? So 1 times the power of minus, or let me just write it like this, minus 3 for the volume, because the volume is in milliliters, so you need to keep that in mind. So times the power of minus 3 times 0.1. You're going to get 1.5 times the power of minus 3. If you need to keep in mind significant figures, then, well, it looks like there's 2 from the 0.1, so, but anyways, it doesn't matter as much. To be honest, I would have wanted the, anyways. So part C, which one would be most useful? We have a range of pHs, so we look here, it's 7. So which one has the, like, the 7 embedded in it, or like, you know, the closest to the 7? No. Oh no, actually, no. This one doesn't even have it, so this is the best choice. It has it right here. It's not too far and stuff. So if you have, let's say, they won't give you something hard, but let's say if they have like 6, say, to 7, and another one 6.5 to 7.2, I prefer if you pick this, I guess. But like, again, they want to ask you these questions. Just anyways. So compare the endpoint with the equivalence point. So this is important. The endpoint is basically what is done experimentally. So it's going to be the change of the color of the indicator. The equivalence point is the theory behind the chemistry, I guess. So it's going to be where the reactants, which is basically the acid and the base, they're fully reacted with each other, have been fully consumed, fully reacted with each other. And yeah, that's where the equivalence point is, when they're fully reacted with each other. So fully consumed, fully reacted. Another student, blah blah blah, what did he do? He reversed the solutions. He swapped them. The burette, the one that was in the burette is in the conical, and the conical was in the burette, and so on. So it's basically, you start with an acid, so you're gonna start with a base. So you might have somewhere around here, say. And yeah, so you're just gonna have inverted. So here you're gonna have the curve being like this, You're gonna have somewhere here like this, and this is where it goes. So it's just inverted. As you can see, it's just inverted. Just literally take this, flip it, and you get that. And that's it. So yeah, that's it for part E. Okay, so number 4. This one's nice, but some questions are tricky. But it's good because you can answer them quickly. Unlike the previous questions, especially the ones in the top questions. So pH at this point is less than 3. Which one has pH less than 3? Definitely not this, definitely not this. These are suspicious. But on the safe side, we're looking for 1 point, and it's less than 3. Pick the safest one, the lowest one. So A. So the answer for this one's A. And then pH greater than 8, but less than 10. Less than 10, but greater than 8. Say someone this is 10, someone this is 8. So you're going to have this be the most clear points. So D. pH at this point could be used to determine the acid dissociation constant. You might think of the pH one, but if you remember, we're talking about, look at this. This is a buffer. This is a buffer. Yeah, this is a buffer. It doesn't, it tells you weak monoprotic acid. But anyways, because of this, if you see this in DC, you notice this and that. So you have a buffer. It's not instantly like this, or like, can't draw it well. But anyways, so it's not like that. Like when you have, you have like this, and you have like that. It's not like this. It has a bump, and then it goes like this. So it's a weak. One of them is weak, and here we have a weak acid. Because of that, you have something called a half equivalence point. The special part about it is that it's the pH will be equal to the pKa, and then from the pKa you can get the Ka, which is simply minus log. This is minus log of the Ka. So to get Ka, do 10 to the minus of the pKa, just like how we find the concentration of H plus by doing 10 to the minus of pH. Same thing. So yeah, and if you want to know why is this the case, because this is the point where both the acid and the base, the weak acid and the weak base, that's the conjugates basically, are in equal ratio. And we know that plus log blah 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 base over acid is 1, log of that is going to be 0, log of 1 is 0, so you're going to be left with this. So again, the point is B. Optimum buffer action, where they have ratio of 1 to 1. Again, B, have equivalence point. Buffered, when it has maximum capacity, so B. Of the blah, 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 the point where solution is most basic. Just most basic. Here we go, we become more basic. Here we go, we become more acidic. Which one is the most basic? You read like this, and you reach E. The most basic. So yeah. It's going to be, as they answered it actually, E. So which of the following blah blah equivalence points? So again, it's D. Indicator is best. So we look at D. D looks like 8.7 is nice. Which one has it best? No. This one. It has 8.7 somewhere here. And again, it doesn't have to be 8.7 because 8.7 might be here. Again, it's close actually, but anyways. So it's somewhere around that. So look for the best one. So it's going to be D, and that's it basically.